Okay, today let's take a look at the mean value theorem for derivatives. It's kind of a verbose statement here. Let's read it and see if we can make some sense out of this. First of all, it says that if a function is continuous on a closed interval from a to b, and you can take the derivative on the open interval a to b. In other words, at the endpoints, you may not be able to take the derivative, but in between you can. And there exists a number c in between a and b such that the derivative at c, or the slope of the original function, is equal to the slope of the secant line at the endpoints. Well, this seems a little bit strange to us, but let's just take a look at the picture of it, and I bet it makes a little more sense for us. So we have, let's see, let's just do it over here. We'll call this A and B, and let's just draw any old function here. Let's do it purple. So what they're saying is, if you have some sort of a function, and it's any function, as long as you can take the derivative, what they're saying is that if you draw a secant line there, its slope is going to match up with the slope of a tangent line at least one time in between here. So perhaps right here it matches, and maybe again over here it matches. And once again, these values would be, you know, some value, they call them c. So in other words, the slope of the secant line matches the slope of the derivative. Alright, well, I hope my illustration didn't throw you off too much. Now, let's take a look at an example of this without a graph. Okay, so this is saying that we have this function, find all the values for c between 1 and 4 that satisfy this equation. So I guess the first step we could do is to find the slope of the secant line. The slope of the secant line would be using these two x values to find the slope. So in other words, we're going to take the function value of 4, subtract the function value of 1, and then the x's on the bottom. So we have rise over the run. So this is going to equal 3 on the bottom. So let's take a look at the function value of 4. So we have 5 minus 4 over 4. Well, that's just equal to 1. So 5 minus 1 is 4. And 5 minus 4 over, plugging in 1, 5 minus 4 equals 1. So the slope of the secant line is 3 over 3, and that's equal to 1. So in plain English, what they're asking us to do is take the derivative and set it equal to 1, and find all the values for x that are in between 1 and 4 that make this true. Alright, so let's switch colors here, and let's take the derivative of this function. That's equal to 0. And maybe we need to rewrite this function. 4x to the negative 1. Sorry about that. So we have 5 minus 4x to the negative first. So the derivative of this is 0. The power rule here, you have negative 1 times negative 4, so we have plus 4. And this is what? X to the negative 2, or x squared on the bottom, like this. So what value are we looking to match? We're looking to match this value with 1. So just set the whole thing equal to 1. Just cross multiply here, and you get x squared is equal to 4. Square root of that is plus and minus 2. Okay, well, negative 2 is outside of the range that we're interested in. We're only looking from 1 to 4, so we're just going to have to say that this c value would be what? 2. So if we plug a positive 2 into this derivative, 4 over 2 squared equals 1. Alright. One other theorem that I want to mention, and I haven't seen it being tested very often, is Rolle's theorem. And Rolle's theorem is sort of an extension of the mean value theorem for a specific case. It says that if the function is continuous on the closed interval of a to b, and you can take the derivative on the points in between, and if the function value a and is equal to the function value b, then there exists at least one number in between there where the derivative is equal to 0. I'm not going to give you an example of this, but I will draw a picture and just illustrate this. So we have a value a and b, and what they're saying is that the function value for a is equal to the function value of b. So let's try to get that matched up a little bit. And no matter what the graph looks like, as long as you can take the derivative all along the way, what they're saying is that somewhere in between here, at least one time, there's going to be a derivative that equals 0. And how does this relate back to the mean value theorem? The secant line here, the slope is equal to what? Equal to 0, right? So you can see, let's identify a couple of points here. You can see that the slope of the tangent line would be 0 here and also here. So we would do it the same way. We would just take the derivative and set it equal to 0 and solve and find the critical values, basically. Alright, we'll stop for here.